Recording. Okay. Let's see how my handwriting is this morning. I'm a combination of tired and coffee, so doesn't bode well. But maybe it'll force me to write slowly, which would be good. Here we are. It's the 7th, and we're going to talk about chapter 2, modeling with exponential functions. I think for the 99% of us who aren't pure mathematicians, the most value we get out of mathematics is the ability to model real physical situations with mathematics so that we can then apply our mathematical tools to analyze those settings. So I like to focus on developing a mathematical model for a physical situation. And one of the most common you come across are exponential functions. But let's recall the notation. If I do 3 to the 7th, that's 3 times 3 times 3 times 3 times 3 times 3 times 3. All right, so that's our notation. And you practice combining different ones, and maybe you had something that looked like 4x to the 9th, right? Which is the 4 is out there, and then you have a whole bunch of x's, and I should have picked a smaller number. 7, 8, 9. For simplicity, we focused on using integers, in particular positive integers. But it doesn't have to be like that. We could have like 1.27 to the 4th. That's 1.27 multiplied by itself 4 times. We're not constrained to only look at integers. And in fact, very few modeling situations will have an integer as the base. It will usually have some sort of decimal or maybe a fraction. So with that in mind, let's consider how to model percentage growth. And what I mean by that is let the output grow by, for example, 27% each time. So if I started with one unit, after one step, it increases by 27%. So now I have the 1 plus that extra 27%, right? What I started with plus 27% more, which I could combine and just write as 1.27. After another step, the new amount increases by 27%. Well, my new amount is 1.27, right? Plus 27% of that. 27% of 1.27. So it's not that I'm adding 0.27 each time, right? I'm increasing it by 27% each time. And with a little mathematical recombination, that's 1.27 times 1.27. So percentage growth is repeated multiplication. After 3 steps, I have 1.27 times 1.27 times 1.27, which I could rewrite as 1.27 to the third. So that means percentage growth is exponential. So anything that grows by percentage growth, anything that grows by repeated multiplication is exponential change. Anything, let me just write anything. Anything that grows by percentage growth or by repeated multiplication is exponential growth. A bacterial colony grows by 27% each day. That's 1.27 to the number of days. Okay. Now, that's my basic exponential growth idea. I take a base and I raise it to a number of powers. But what if that bacterial colony starts off at a certain size? All right, so this kind of just describes the growth. But what if you have a bacterial colony has 5,000 members each day? It grows by 27%. We can now model this. This is our verbal representation. And the key in a verbal representation is you're almost always going to see some kind of percentage change. The only time you don't see a percentage change if it says something like it doubles, but that's still a constant multiplication, right? That's a repeated multiplication. So that's our verbal representation. We can do a table representation. I think table representations are an excellent way to represent exponential functions because they really allow you to see the repeated multiplication. If X is the number of days and Y is the number of bacteria or number of members, at the beginning, how many bacteria members do we have?
1,000.
Okay, so we'll put 5,000 there. And what do I want to put for X?
0.
0, because that usually represents the beginning, especially when you're talking about time. Now I'm going to increase my days by 1. So X becomes 1. What's going to happen to that population?
Increase.
Then it increased by 27%.
It's going to increase by 27%, which we represent as multiplying by 1.27. And a calculator can figure that out for us. 6350. And after our next day, again, we increase our days by 1. What are we going to do to our population?
Increase it again.
We're going to increase it again with repeated multiplication. So we're going to multiply by 1.27 again. We get 8,064 approximately. Right? I don't really care if it's 864 or 865, they're bacteria, they're tiny. So this is how we would represent an exponential function with a table. You have your inputs on one side and your outputs on the other. And I like to annotate it by showing that multiplication. By showing that repeated multiplication. If we go one more, we're going to multiply by 1.27 again. We get 10,242 approximately. Right? Let's do a symbolic representation. We can write it as f of x to represent that it's a function. And the way you write an exponential function is you start with the y-intercept. What is the y-intercept from based on our table? Yeah, 0, 5,000. You start with the y-intercept. And what happens every time x increases by 1?
It goes up 27%.
Yep, but let's put in a mathematical operation sense. There we go. We multiply it by 1.27 for every single step. That's repeated multiplication, which is an exponential. And this is what an exponential function looks like with a formula. You have your starting value. This is called the, well, this is the base, but I like to call this the exponential rate of change. And it's also commonly called the multiplication factor. Because it's the number that you're multiplying by. All right, and now let's do this graphically. Our scale is going to be crazy because 5,000 is a lot. There's X, here's Y. What's the height of that point on the Y-axis?
5,000.
Exactly, because that's the y-intercept. And then after one day, we increase to 6,350. And after 2 days, we're not going to add the same amount, right? It's not repeated addition, it's repeated multiplication. So this is actually going to grow a little bit faster the next time. Well, the growth rate's going to be the same, but the increases are going to be a little bit bigger. It's going to jump up to 8064. And then after 3 days, it's going to jump up even more, all the way here to 10,242. And if we imagine, it's not like at stroke of midnight, all the bacteria split, right? They're growing continuously. So we can connect all of this with a nice smooth line, and what we get is a function that curves up like that. And if we were to extend it down, which we probably won't in this case, we're talking about bacteria starting from day 0, but it'll curve down toward the x-axis like this. It actually never touches. An actual exponential function, basic exponential function, will never actually touch the x-axis.
Does it always have a y-intercept at certain point?
It always has a y-intercept, yep, and it never touches the x-axis. The y-intercept is always the point where x is 0. It's always your initial value. Growth, the growth rate will be constant. The amount that it goes up gets bigger and bigger and bigger each time, so it curves up. It actually keeps going forever, even though it looks like it's going to go up. It just grows so fast, we can't show it all.
How do you know it's not coming the other direction? Coming down because it's getting closer and closer to 0 on the, or
How do I know it's not doing this?
something going down this way versus going this way?
Well, based on, first of all, based on my table, I see as x increases, the y's increase. Second of all, based on my word, it grows by 27%, so it should get
Oh,
bigger.
yeah, I guess.
Yeah, and we're also going to look at the other version, which is called decay. Actually, we're going to do that right now. The value of pets.com stock was $100 per share every month. The value dropped by 18%. Scott probably remembers pets.com, maybe. Big deal in the year 2000.
Too many.
Yeah, and then the dot-com bubble burst. How many of you were born after the year 2000?
Everybody.
Most people, not all of us though, right? Some of us remember pets.com as a good idea that didn't work, but now there's Chewy and of course Amazon, right? So it wasn't that it was a bad model, just the wrong time. Okay, so let's explore this using a table again. I think that's probably a good way to do it. It's going to give us some intuition. So let's do X, which is months, and Y, which is value in dollars. How much was it worth at the beginning?
Okay.
Okay. That's okay. It's also a poorly written 100. And so that was at the beginning, so we'll say X equals 0 then. Now we increase by a month. And what's the new value of the stock? 82. 82. So here's the key. If it drops by 18%, you're taking away 18%, which means it left 82%. And this is a constant multiplication. So what's the multiplication factor from here to here? How do you go from 100 to 82? You're going to multiply by what number? Well, not 0.18. That would bring you all the way down to 18, right? 0.82. This is the challenge with decay. Let me show you. All right, so we start with 100. And we said it decreases by 18%, right? It drops by 18%. So if I multiply by 0.18, that doesn't make any sense. That's not an 18% decrease. That's a giant decrease. how do I get from 100 to 82? I multiply it by 0.82. So the particular multiplication factor here, it's not 18 or 0.18. It's 1 minus 0.18. Just like this one, the multiplication factor was 1 plus 0.27. 27% increase, 1 plus. 18% decrease, 1 minus. That's the biggest challenge. And so when you take your midterm and you have a multiple choice option, you're going to have one that says it's decreasing by multiplying by 0.82. You're going to have another one where it's decreasing multiplying by 0.18. And you're going to show me that you understand the difference and which one is correct. I can guarantee that. We increase another month and it drops by another 18%. So what do I multiply it by?
66.66.
So that's the value, right? Because you did it in your head, which is impressive. What was the multiplication that got me from here to here? 0.82 again. Repeated multiplication. And so here I've got, I'll just barely see it. 100 times 0.82 gets me to 0.82, and I multiply it by 0.82 again, and it gets me to 67, which is very close to what you said. Oh, we can't see it on the paper anymore. There we go. And then we wait another month, and by this point we're panicking. We really should have sold earlier, but oh well, it happens. And what do we multiply by? 0.82 again, repeated multiplication. We got 55.14. But let's build a formula from this. The symbolic version. I can do f of x. And remember, I start with my y-intercept, which was what? 100. And I multiply by the multiplication factor, by the base, by 0.82, raised to the power x. This is a multiplication factor. That's the multiplication rate of change or the exponential rate of change. And if we show it graphically, we started at $100. After a month, we've dropped to $82. I know the scale is not great, but I want to show the curvature. After another month, we go down by 82%, but we're not decreasing by the same quantity. So it does go down, but by not quite as much. Down here to 67. And after another month, it goes down again, but by not quite as much, to 55. And so we get something that curves down towards the x-axis like this. There's pets.com. It actually does kind of look like it, right? It's not perfect, but again, nothing in life ever matches perfectly. And it didn't start at 100, it started at 11, but I just picked that number randomly. And you see it gets close to 0, but it's never going to get all the way to 0 probably because somebody's going to be willing to take a chance on it. this exponential function never touches 0. Never touches the x-axis. And the other direction, it would go up and up and up forever. And again, this is a real physical situation, which is why we started here at x equals 0. The function itself goes forever, but the domain doesn't make sense. I mean, if we started in the year 2000 and we went by month, we wouldn't go out to infinite months because we haven't been infinite months. It's however many months it's been since the year 2000. 144 plus 12, 156. We only get out to x equals 156. That's how many months it's been. Okay. So that's exponential decay. Exponential decay as opposed to exponential growth. But both of them work by repeated multiplication. By percentage changes each time. Good. All right, let's compare linear functions to exponential functions. And we're going to compare them in all 4 of the representations. I'll probably do, I'm going to do the table form first. Compare linear to an exponential. Give yourself a little bit of space above your 0 on each of those, enough to write 2 other numbers. All right, let's pick when x is 0, let's make y equal to 5. And in a linear function, when x increases by 1, we're going to add a certain amount or subtract a certain amount. So we get to 8. And if x increases by another 1, we're going to add 3 again. Repeated addition or repeated subtraction. And if we add another 1, we're going to add 3 again, and we get to 14. And of course, going the other way, if we go from 0 and now we actually go backwards, we're going to subtract 3. But actually, I don't want to do the arrow that way. I still want to go up by 1. I think it's important to know that that's always repeated addition. So that's 2. And that must be -1. Let's build an exponential function that's very similar, because the numbers are all going to start off looking pretty much the same, but it's going to change. So let's say with our exponential function, we start at 5. But this time, when you add 1 to the input, what do you do to the output? Do you add or you multiply? You multiply. Let's multiply by 3. That takes us to 15. And then we multiply by 3 again, which takes us to 45. And we multiply by 3 again, which takes us to 135. And if we think about negative x values, we're going to get 5/3. And here, oh, sorry, that's still multiplied by 3. Still multiplied by 3, 5/9. Let's do the symbolic next. Linear y equals mx plus b. Exponential y equals b times a to the x. These are just letters. And in your homework, it uses a different arrangement of these letters, but I prefer this one. B is what? And y equals it. That's the y-intercept. And it's the same for both. That's why I like B there. It's still your y-intercept. In a linear world, m is what?
Slope.
That's your slope. That's your addition rate of change. Right, it's how much you add each time. And in the exponential world, a is your multiplication factor. It's how much you multiply by each time. So let's use these same functions here as we had in table form. Tables are really nice for identifying slope and intercept because there's our y-intercept right there, 0, 5. And our slope is the +3. So m equals 3, b equals 5, y equals 3x plus 5. And in the exponential world, a equals 3, b equals 5. And again, you can just read that off. There's the b equals 5, and there's the a equals 3. So y equals 5 times 3 to the x. Okay. Verbal. I have 5 apples. Each day, I pick 3 more apples. Is that linear or exponential? Linear, because I'm adding 3 each time. Linear. Exponential. I have 5 puppies. Each day, I get 3 times as many puppies
Lord help me.
as I had the day before. So this is an example where it doesn't look like a percentage change, but it's still a multiplication, right? It's a constant multiplication. Not a lot of things grow by integer multiplications every time. Most things grow by a percentage change every time, which is why it's more common to see something like 1.27 than 3 as your base when you're actually doing an application. Okay. And let's do a graph. Linear. X and Y. Exponential. Our scales are probably going to be different, but that's okay. Here's 5. And each day I add 3 more. And if I went back the other way, I'd be subtracting 3. Linear because it's a line. Exponential. I start at 5, and then I triple, and I'm up to 15, and then I triple, and I'm up to 45, and then I'm triple, and I've blown way past my scale.
Out dog food.
and dog food. I have no more dog food. Now, if we went the other way, you can check your table. But if I'm multiplying as I increase X, I'd be dividing as I decrease X. So now I'm down to 5/3 and then 5/9. But notice, no matter how many times I divide by 3, it's still going to be a positive number. Because if you're dividing by a positive number, you're still going to have a positive number. I never actually get to the x-axis. But we can't really tell. At a certain point, I'm not going to have 5/81 of a puppy. This is exponential growth compared to linear growth, but you could also do the same thing with exponential k and linear decay. Right, okay, I think. All right, two more ideas. Building exponential functions. The symbolic usually from different representations. We've already did this with verbal. Verbal to symbolic. You look for the initial value and the percentage change, which I've done, so I'm not going to do again, and convert to a multiplication factor. Table to symbolic. Actually, we just did that as well. Find the y-intercept, find the multiplication factor. Find the y-intercept, find the multiplication factor. Let me do another example of that. Example. I'll do two different examples. Here's one. So we've got 0, 8, 1, 13, and I tell you I want an exponential function. Could I build a linear function from these 2 points?
Yeah.
Yeah, I could. It would have a y-intercept of 8 and a slope of 5. So actually knowing 2 points doesn't tell you if it's linear, exponential, or any other function. You need more information. So if I want an exponential function, I need y equals b times a to the x. So I need b and I need a. B is the y-intercept, which is what?
8.
8. So that part's pretty straightforward. There's my y-intercept, 8. A is the multiplication factor. So it's the number I multiply when I increase x by 1. But that's not obvious to me. All right, it's like, I don't really know. It's not doubling. It's not like another 0.25%. But there is a pretty simple way to do it, which is if I want to get from 8 to 13, I can multiply it by 13 over 8. Because 8 times 13 over 8, those cancel, gives you your 13. So A is 13/8. And so it tells me that my function is 8 times 13/8 to the x. And I could convert that to a decimal if I wanted to, but I don't have to. It's still the multiplication factor. There's one example. Here's another example from the table. Let's see. 4. $72. Hold on. 216. All right, and I want this to be exponential. So I want it to be y equals b times a to the x. So I need b and I need a. Can we read off what b is?
Right?
Can we read off what b is? I don't disagree with you necessarily, but can we read off what it is?
No.
No, because there's no 0 for the x. Right? A good table will give you the starting point, but not all tables give you the starting point. So we don't know b yet. But can we figure out what a is? Yes, because I know if this goes up by 1, that goes up by a multiplication factor. What is that multiplication factor? Well, the simplest thing is just to say it must be 72/24, because that's how you get from 24 to 72 with multiplication. And you might as well check and see if that comes out to be a nice simple answer, and it does. 72 divided by 24 is 3. So A is 3, excuse me. And now we can work our way backwards to get to 0 using the table. If x is 2, what is y? It has to be 24 every single time because it's a function. And I can put it in my table more than once. That's no problem. So about if x is 1, what is y? It must be 8. Because 8 times 3 gets me to 24. And so if x is 0, what is y? What's that? No, because 0 times 3 wouldn't get me to 8.
That's 2.
Well, 2 times 3 is 6. What if I just did this? 8/3.
6.
Yeah. And you found that because you did 8 divided by 3. Right, so you can use your table. Some people might call this guess and checking, but I say this is using a numerical representation. All right, if I know what my x is when, or if I know what my y is when x is 2, and I know it changes by multiplication, I can work my way backwards to figure out what y is when x is 0. So b must be 8/3, and my formula must be y equals 8/3 times 3 to the x. And I put some parentheses around the 3 to the x to make it a little more clear. All right, so that's definitely a step up in complexity, but the same ideas apply. You find your multiplication rate of change, and using that, you can figure out what your y-intercept is. Right? Let's look at how to do it with a graph. Now, I don't have a printed graph here, but that's okay. Because you really only need two pieces of information when you have the graph of an exponential function. This one's going to be decay. All you need is the y-intercept, and you need the y value when x is 1. Because your formula is y equals b times a to the x. What's b?
Well,
It's the y-intercept, which is 12. And a is whatever you multiply 12 by to get down to 8. This is the multiplication factor that moves you from 12 to 8, which is 8 over 12. Or 2/3. How do I get from 12 to 8 with multiplication? Right? You get from 12 to 8 with multiplication, you multiply by 2/3, and that's your multiplication factor. So as long as you're stepping up by 1, then you can just find your multiplication factor by looking at your y-axis. So graphical, I would say it's not really graphical. What you're really doing is you're building a table from the graph that looks like this. 0, 12, and 1, 8, and they're using your table. Because if you're trying to get from graph to symbol, no one says you have to go directly there. You can always work through the table to make it a little bit more easy for you. All right, so here we have the graphical, and if it's not clear to you what these 2 points are in terms of the formula, you can go through the table version before you get to the symbol version. And I really encourage that kind of thinking. There are a couple like this on your worksheet, and you might raise your hand and say, I'm not really sure what to do here. I'm going to say, have you tried making a table? All right. Last thing, doubling time and half-life. All I'm going to say, and there are videos that go into depth on this, is doubling time means the multiplication factor is 2, and half-life and the multiplication factor is 1/2. Half-life is more common in physical applications. Have you ever heard of carbon dating to see how old an archaeological dig is? They're measuring the amount of radioactive carbon left in a branch that they found there, or a seed or something organic. And by measuring the amount of radioactive carbon, which decays at a certain rate by percentage, they can figure out how old that archaeological site is. But let me give you a verbal example. carbon 14 is what's used most often, but it has a half-life of like 28,000 years. I'm not going to use that. Let's use Rapidium. Has a half-life of 13 days, which means half of the Rapidium decays after 13 days, i.e. half of the Rapidium will decay every 13 days. If you have a sample with 50 grams of Rapidium, make a symbolic representation of this situation. We'll get to the symbolic, but I'm going to work through the table because I think it's a little simpler. So let's start with a table representation. Oops, that's an X, days, and Y is grams. On day 0, how much Rapidium do I have? 50 grams. Cool. Do I know how much I'll have on day 1? I don't. This doesn't give me any information about what happens on day 1. What's the information it gives me?
What happens on day 15?
What happens on day 13? So let me just put 13 in for X. Can't see it, but sorry. Half-life is going to be decay. So after 13 days, I've lost half of it. So how much is left? 25. What's the next X value I should put in?
32.
Hmm?
26.
I'll do 26 because that's another 13 days. Notice the half-life is now adding 13 each time instead of adding 1. And then I'll have 12.5 grams left. So if I want to make a formula, I have to add one extra piece of information. Y equals B times A to the X. So far it's the same, but I have to change my exponent. I'm going to divide it by the half-life. B is the y-intercept. What's that number? 50. If I'm a half-life situation, what should A be? 1/2, right? Because it's multiplying by 1/2 each time. And what is my half-life? How many days? 13. So up in the exponent, I take X and I divide it by the 13. Because it takes 13 days in order to multiply by 1/2. And generally, the formula would be B times A to the X over C. That's the letter I use, where C is the half-life. B is the initial value. A is always going to be 1/2 for the half-life. And C is the number of days in the half-life. There we go. So you'll get some practice with that. Anybody have questions? All right, let me stop the recording. And hand these out. Absolutely. Let me hand out the name tags. Oh. Apologize. It is Caitlin, but a different Caitlin. I don't think I have a name tag for you. Would you make one, please? That way I can get you the right.